In this video, we work a couple more examples of first-order linear ordinary differential equations. We're going to solve them with integrating factors. This first problem is from the Differential Equations, a Primer for Scientists and Engineers by Christian Constanda. It's published by Springer. And it's from the first edition of the book. The differential equation is t squared plus 1 times y prime minus t times y equals this function of t. And we've got an initial condition as well. So first of all, I notice that it's a first order linear differential equation. It's first order because the highest order derivative is the first derivative. It's linear because that first derivative is raised to the first power. That y is raised to the first power. The coefficient functions only depend on the independent variable t, and the function on the right-hand side depends on t. So this is a first-order linear equation, and it can be solved with an integrating factor. So we're just going to follow the method that we talked about in the last video. The first step in the method is to write the differential equation in standard form. And standard form, recall, it just looks like this. You've got the derivative by itself. In this case, y depends on t, so this is dy dt, plus some function of t times y. So that's all on one side. And then you have a function of t on the other side. So we just want the coefficient of dy to t to be 1. And then we want to have a function of t times y added to it, and then a function of t on the other side. So we're almost there with this. We just need to divide both sides by that coefficient of y prime. And remember, y prime and dy dt are the same thing. So we're going to divide both sides by t squared plus 1. And now the differential equation is in standard form. I've got y prime minus t over t squared plus 1 times y equals 2t times t squared plus 1. Now, once you've written the differential equation in standard form, our next goal is to find that integrating factor. I'm going to abbreviate that IF for integrating factor. And the way we do that is we identify p of t, that function in front of the y, and we take its antiderivative. And then we define the integrating factor to be e raised to that power. So our p of t is this. Make sure you include that negative sign. So we identify p of t, then we just compute its antiderivative. I look at this, I say to myself, do I have a rule for that? I don't. And then I ask myself, will u substitution work? And it sure will. If I let u be the denominator, then du is just 2t dt. And I'm not so worried about the 2. I have a t dt up there as a factor. So this is going to work. If I see that function of t times dt that I need up there, I know the u sub will work. I can always adjust the constants. Because I don't need the 2, I'll divide both sides by 2 here, or multiply by 1/2, same thing. And then we'll rewrite the integral entirely in terms of u. So that -1 is still there. That t times dt can be replaced by 1/2 of du. Because when we make the substitution, they are exactly the same thing. And I've got a u right here. Now, you might be tempted to just go on from here and use the power rule for that, but remember, this u is not just a t squared plus 1 by itself. It's a u in the denominator. There's an implied 1 up there. So don't use the power rule on that. Remember that when you take out that t times dt and you replace it with a 1/2 du, there's still an implied 1 in the numerator, or an implied -1 if you prefer. So now we ask ourselves, do we have a rule for this? And we sure do. The antiderivative of 1 over u is natural log of the absolute value of u plus c. For reasons that we discussed in another video, we're going to choose this c to be 0. We just need a single integrating factor. We don't need a family of integrating factors. And then of course, with our choice of c being 0, we will back substitute. And u is t squared plus 1. And of course, t squared plus 1 is positive all the time, so we really don't need the absolute value. Okay, so that was the antiderivative of p of t. Now we just want the integrating factor to be e to that power. So we can say the integrating factor is typically denoted by mu. So we'll have mu of t. That's e to the integral of p of t power, or antiderivative of p of t power, with our choice of c equal to 0, because we don't need infinitely many integrating factors. We just need the one. So that is our integrating factor. But I notice immediately the presence of that e and that natural log, and it really makes me want to cancel them, because we know that exponentials and logarithmic functions, when they have the same base, they undo each other. They're inverse functions. That's why, well, that is the definition of the logarithm. It was invented to undo this exponentiation. So we want to simplify this, but we can't simplify this with that -1/2 out front. You have to recall some rules from algebra in order to get rid of that -1/2. Remember this rule: if you've got a constant in front of natural log of a, you can bring that constant inside and make that natural log of a raised to the n. That's exactly what we want to do here. This is, we're going to bring that -1/2 inside, and this is e raised to the natural log of t squared plus 1 raised to the -1/2. And the reason for doing that is because when there is a coefficient of 1 in front of that natural log, if I have e raised to the natural log of a power, since those undo each other, we just get a back. They're inverse functions. First, I'm taking the logarithm, and then I'm undoing that by taking the exponential of the result, and I just get what's inside back. So the e and the log reduce, and we end up with a t squared plus 1 to the -1/2. That's our integrating factor. Now remember the brilliance of Bernoulli. He said, if you take this differential equation in standard form and you multiply by this, then the left-hand side will always be the product of y, or the derivative of y times the integrating factor. So that's the thing we do next. We multiply the differential equation in standard form, which I think I'll call dE star. Let's label that, just for the sake of having a label. So I have my original dE, now this is dE star. I'm going to take dE star, and I'll multiply it by my integrating factor. Now this that I'm doing on the left-hand side is just a little notation for me. It helps me keep track of what I'm doing. Of course, we can always just follow the annotation on the right-hand side. That also helps us keep track of what we're doing. So we've got y prime, or I prefer Leibniz notation, dy dt, minus t times, or t divided by, excuse me, t squared plus 1 times y equals 2t times t squared plus 1. And we're multiplying everything by this integrating factor of t squared plus 1 to the 1, or -1/2, or you can call that 1 over t squared plus 1 to the 1/2. I think that's what I'll do here. So I'll multiply by 1 over t squared plus 1 to the 1/2. And then here I'll multiply by 1 over t squared plus 1 to the 1/2. Maybe add some parentheses there just for emphasis. And then I would multiply this by that fraction as well. But remember, dividing by t squared plus 1 to the 1/2 is the same as multiplying by 1 over it. It's the same thing as like dividing something by 2 is the same thing as multiplying by 1/2. With that in mind, I can just divide this guy by t squared plus 1 to the 1/2, and that's going to be equivalent to taking this and multiplying by 1 over that. Okay, so we multiply the dE in standard form by the integrating factor, and then we simplify. And just to make it a little bit easier to check our work, I'm going to write that as t squared plus 1 to the -1/2 again. And then I've got a minus here, I've got a t here, Now there is a t squared plus 1 to the first that was already there times a t squared plus 1 to the 1/2. Remember how that works. If the bases are the same, you add the exponents. The bases are t squared plus 1 here. So we're going to add the exponents. 1/2 plus 1 is 3/2. And if I bring that up to the numerator, that's going to make that a negative 3/2. That's just using this rule. If you've got 1 over x to some power, that's x to that same power but negative. And then over here, I've got x, or an expression to some power, divided by an expression to a different power. Well, you keep the base and then you just subtract the exponents. So I'm going to have a 1 minus a 1/2. That's going to give me a 1/2 power. Okay, so that's my simplified differential equation. Now, if we've done everything correctly, Bernoulli said, if you do this, if you multiply by this integrating factor, then the left-hand side should be the derivative with respect to your independent variable, which in our case is t, of y times the integrating factor. Oops, I lost an exponent there. Now you should always check this out. This is sort of an algebraic aside, little algebra review. Back to diffie. At this point, we want to recognize and possibly check that the left-hand side is equal to the derivative with respect to t of y times the integrating factor. You can use y times mu if you prefer that notation. Now, I always like to check this. Now, we can check using the product rule. If this is my first function and that's my second function, according to the product rule, I should get derivative of the first times the second. Derivative of y with respect to t is there, times the second. So that's good. Derivative of the first times the second, plus derivative of the second. So that would be this piece, I guess, times the first. The first is there. So the way we can check this is we can take the derivative of the integrating factor. If the derivative of the integrating factor is this, so that this is derivative of the first times the second plus the derivative of the second times the first, then we know we've done this correctly. If not, if that doesn't check out, and sometimes it's just the sign is wrong, like you're so close, but that's a minus, and when you take the derivative, you get a plus. Be careful of that. If that happens to you, that means something up here went wrong. Maybe your antiderivative was wrong. Maybe you forgot the minus in your P of t. Maybe you made an algebra error when you were trying to simplify your integrating factor. So you always want to check this step. And the way you check it is by using the product rule and making sure that the derivative of that second function is that function that's right in front of the y. So let's check. I'm taking the derivative with respect to t of t squared plus 1 to the negative 1/2 power. And so I've got all of this inside that power function, that u to the negative 1/2. Well, according to the chain rule, we take the derivative of the outside first. So we bring my 1/2 down, then we take our original function and we subtract 1 from the exponent. So bring the power down, and then you subtract 1 from the exponent. So we have 1/2 minus 1, that's going to be negative 3/2. Then you plug the inside function back inside, and then you multiply by the derivative of the inside by the chain rule. The derivative of the inside is 2t. Check it out, the 1/2 and the 2 reduce, and we end up with a negative t times t squared plus 1 to the negative 3/2, and that's exactly what we have there. So we know we did our algebra correct, we know we did our anti-differentiation correctly, and this left-hand side actually is what it's supposed to be. And yeah, that was the brilliance of Bernoulli. He said, do that, and that will get you here. You can say, well, why is that brilliant? Because we're trying to get y by itself, remember? We had this thing, it had a y prime here and it had a y there, and it was really hard to get y by itself. But if I multiply by that integrating factor and I'm here now it's really easy to get y by itself. all we have to do is undo a couple of operations, and then we can get y by itself, and that would solve the differential equation. So let's look at that. I have the derivative with respect to t of y times t squared plus 1 to the negative 1/2 equals 2t times t squared plus 1 to the positive 1/2. And we're trying to get y by itself. And it's multiplied by this, and then we take a derivative. Well, the way we undo that is we undo the last operation that was done first until y is isolated. So we've got this derivative all the way on the outside. To get rid of derivatives, we anti-differentiate both sides with respect to t. Because the antiderivative of the derivative is the original function. And we just end up with y times this t squared plus 1 to the negative 1/2, which I think I'm going to write it now as 1 over t squared plus 1 to the positive 1/2. And that equals this antiderivative over here, this function of t. So we've done that. Now let's finish this side. Do the computation over there. We ask ourselves, do we have a rule for that? It's a product, so no, we don't have a rule for that. If the basic rules don't work, we ask ourselves, does U substitution work? And it sure does. I've got a t squared plus 1 there. It's inside that square root function, or that 1/2 power function. So let U equal that to compute du. That's 2t dt. And check it out, there's a 2d dt right there. So this is going to work just fine. So I've got a u to the 1/2 and a du right there. Remember how u sub works. You want to write everything entirely in terms of u. That's u to the 1/2. 2t dt is the same as du. So we're replacing that with du. And now we say, do I have a rule for that? And we sure do. We just have the power rule. So you add 1 to the exponent. You divide by the new exponent. Dividing by 3/2 is multiplying by 2/3. Don't forget to add your constant of integration. And then back substitute. U is just something that we made up so we could take an antiderivative, right? So we plug that function of t back in. And now we're here. We've got y divided by t squared plus 1 to the 1/2 is equal to all of this. So I said Bernoulli was brilliant. Multiply by the integrating factor. Then the left-hand side will give you the derivative of this product. To get rid of the derivative, you take the antiderivative. Now you've got this equation. You're trying to get y by itself. Just solve for y. So you would divide by the integrating factor in general. In this case, we've got this factor in the denominator. So to get y by itself, we'll multiply both sides by that factor in the denominator. You're just solving for y. Now this has 2 terms. Don't forget it has 2 terms. A lot of people just take this and multiply it, this by this and then just say plus c. You don't want to do that. That c gets multiplied by the integrating factor, or 1 over the integrating factor as well. So we're going to distribute. Now you've got some expressions with the same base. Add the exponents. 3/2 plus 1/2 is 2. 4/2. 4/2 is 2. And we've got c times t squared plus 1 to the 1/2. And that is the general solution of this first order linear differential equation. Now, usually whenever we find the general solution, we also want to find an interval of existence. So I would just go through the method and look for any t values that are disallowed by the algebra and the calculus that we did. When we initially divided by t squared plus 1, we need to make sure that t squared plus 1 is never 0. And actually it's not. It's always greater than or equal to 1, right? Because t squared is always positive, except for when it's 0. So there's no way that's going to be 0. So we're fine there. Here too, we can't let u be 0, but use t squared plus 1, so it's okay. We can't take the natural log of 0. Well, t squared plus 1 is never 0, so we're okay. Same thing here, same thing here. We do have fractions, but every time we have a fraction, it involves a t squared plus 1 in the denominator. And again, it's never 0. So as I look through the method, I don't see any problems with dividing by 0 at all. So I think this should work all the time. So this is our general solution on the interval from -infinity to infinity. So I will label that GS for general solution. And we always want to provide an interval of existence. And the maximal interval of existence in this case is -infinity to infinity. Now, we were given an initial condition. Remember how this works. This is enough information to get us the value of that arbitrary constant C. This is going to pick out one member of that family of solutions and say, I want the member of the family that satisfies this. I want the member of the family for which y is equal to 2/3 whenever t equals 0. So find me that member of the family. That's what this question is asking you. So first we find the family. We say, okay, these are all of the guys, all of the solutions that satisfy this differential equation. And now we want to pick out the particular member of the family that satisfies that. So to do that, we're going to use the initial condition to find the value of C. It's actually pretty easy. You replace t with 0 because we were given that t equals 0. Simplify as much as possible. Of course, that's just 1 times 2/3, that's 2/3. And that's 1 times C, which is C. That's our answer. That's y of 0 in general, regardless of what the value of C is. And then we're going to say, we want the value of C for which y of 0 equals 2/3. So we take this and we set it equal to 2/3 and solve for C. Well, if 2/3 plus C equals 2/3, then we know C must be 0. Now you're not finished yet. You haven't told me the solution to the initial value problem yet. We want the particular solution of the IVP on an interval I. The way you find that particular solution is first you find the value of C and then you plug it into this solution up here. So that was our general solution. If it was just the differential equation, we would be done when we get to here, but because we have an initial condition, we want to substitute in C equals 0, which means that term is gone, and we get this. That is our particular solution of the initial value problem. Okay, so now we're going to look at one more first order linear differential equation. This is problem 2.3.19 from the Fundamentals of Differential Equations book. And I'm sorry, Professor Nagle, that may not be how you pronounce your name, and I apologize if I'm mispronouncing it. But that's the first author, and it's the 9th edition of that book. We've got this differential equation along with an initial condition. Let's check and make sure it's a first ordered linear equation first. Notice that x is our dependent variable, and x depends on t. So I've got the derivative of my dependent variable with respect to t, derivative of x with respect to t right here, and x right here. So the derivative is raised to the first, x is raised to the first. The coefficient functions depend on t, and the right-hand side depends on t. And I've got an initial condition. So looks pretty good. It's first order linear. Let's just go through the method then. First thing we want to do is we want to write the differential equation in standard form. I'm going to call that dE star. So I'm taking this guy and I'm dividing everything by t squared. So I've got dx dt plus, over here, one of the t's will reduce, 7 over t times x equals this. I'll simplify this as well. I've got a t cubed divided by t squared. And then I've got a 2 divided by t squared. Because I've got 2 terms in the numerator, I can just separate the numerator and I can divide both of those by t squared. One of the t squareds will reduce there. And now we're here. So the differential equation is equivalent to this. And of course, this is for t not equal to 0. But t equals 0 is not in the domain of that function on the right-hand side anyway. Okay, so we're here. We've written the differential equation in standard form. And remember what that is. It's the derivative, in this case, x depends on t, plus a function of your independent variable t times your dependent variable equals a function of the independent variable t. So that's the standard form with a dependent variable of x and an independent variable of t. Now I'm just looking at this and I'm identifying p of t. And the reason for that is the next thing we want to do is find that integrating factor that Bernoulli came up with. And the way we find it is we identify p, we compute its antiderivative, and then we define the integrating factor to be e to that power. And there may be some algebra involved. Okay, so I've got my p of t. The antiderivative of 7 over t with respect to t is 7 times natural log of the absolute value of t plus c. We're going to choose that constant to be 0 for the reasons we discussed in the video over the method. And then we'll define the integrating factor to be e to that power. Now again, if I've got a constant out front, I can bring that inside. Because of this exponent property, or not exponent property, log property. And then because of this exponent and log property, because these undo each other, the exponential and the log disappear, and we have a t to the 7th, absolute value of t raised to the 7th power. But notice that we're working with a natural log of t up here. That's only well defined when t is strictly greater than 0. So we can say that this is equal to t to the 7th. And let's just be explicit about the fact that we're saying that t is greater than 0. It's implied here, but when we start dropping absolute values, we should tell our readers why, or we should at least indicate that we're doing it so that they can think about it for a second and think about, well, why would they do that? And then hopefully they know enough math that that makes sense, or at least they know that there's something to follow up on there. Okay, so we've got our integrating factor. It's t to the 7th. And remember what Bernoulli said. He said, multiply by the integrating factor. And then the left-hand side will be the derivative of your dependent variable times your integrating factor if you've done everything correctly. Maybe he didn't say if you've done everything correctly. That's just something I say to you guys all the time. But it's a really good opportunity for us to check our work. So we're going to take our differential equation in standard form, which I'm calling dE star. We're going to multiply it by the integrating factor and simplify. So I have dE star times my integrating factor is this. First, I'm just going to write my simplified dE star down. And then I'm going to multiply everything by t to the 7th. Multiply every term by t to the 7th. And simplify. One of those t's will reduce, and you have a 7t to the 6th. That's inspiring because of the stuff that's coming up next. If you don't know what I'm talking about, that's cool. I'll explain it in a minute. We multiply these guys. T to the 7th times t natural log of t is t to the 8th. And t squared is going to cancel with 2 of those. We're going to end up with a 2t to the 5th. Okay, now, if we've done everything correctly, Bernoulli said, hey, if I multiply by that integrating factor, I'm going to get my dependent variable, or the derivative of the dependent variable times the integrating factor. And we know in theory it was right because we checked in general whenever we had a p of t there, or a p of x. If we need to see if it actually works for this one. Well, it was a first order linear equation. If we've done all the method correctly, if we've executed it correctly, this should check out. So after multiplying the differential equation by the integrating factor and simplifying, we want to recognize that the left-hand side is the derivative with respect to t of your dependent variable times your integrating factor. And I always like to check at this step. So let's check it out. X is a function of t now. I know it's really tempting to think of it as an independent variable, but it's not. X depends on t. So I've got a product here. If I'm using the product rule, we do derivative of the first times the second. Derivative of x with respect to t is right there. So it's derivative of the first times the second, plus derivative of the second, which is 7t to the 6th times the first. That's right there. So it checks out. So it's good, a very good sign. And we're trying to get x by itself. And what we've done to x is we've multiplied it by something, and then we've taken the derivative of the result. So we want to undo those operations one at a time, starting on the outermost operation first, until we can get x by itself. So we're going to anti-differentiate to undo differentiation. And we're doing this with respect to t. And I'll put some brackets here, so all of that's multiplied by my dt. Just a stickler about those notation things. Okay, the antiderivative of the derivative is my dependent variable times t to the 7th. And then over here, that one's easy, that's just a power rule. But this guy is a little bit trickier. Got a product, so it's not a basic rule. The next thing I ask myself is, can I use u substitution? And I can't. The only function inside another function is t, and I don't want to replace all the t's with u's. That wouldn't make sense. It would just be exactly the same thing with a bunch of u's instead of t's. So we don't want to do that. Since u substitution doesn't work and basic rules don't work, the next thing we try is integration by parts, and integration by parts will work. Now you want to remember, whenever you're doing integration by parts, part of this is u. Everything else is dv. If there is a logarithm in your integrand, that's your u. Everything else is dv. If there is an inverse trig function, that's your u. Otherwise, it's usually the polynomial. But in this case, we've got a logarithm. And I think I'm going to just separate this out for right now. We've got t to the 8th times natural log of t. And we've got the integral, or the antiderivative of 2t to the 5th. So that's there. This one's just a power rule, which is easy breezy. This one's not too bad. We just have to remember integration by parts. So focusing on this one, I'm going to let u be natural log of t, and dv is everything else. So we set up this little table. It's like a little 2x2 table. U goes here, dv goes down here. You want to differentiate u to get du, and anti-differentiate dv to get v back. The derivative of natural log of t is 1 over t. Du is 1 over t times dt. The antiderivative of t to the 8th, just a power rule. Add 1 to the exponent and divide by the new exponent. Now, according to integration by parts, which actually comes from the product rule, it's the result of this, the integral of u dv is u times v minus the integral of v du. So we get u times v, so that's 1/9 t to the 9th times natural log of t minus the integral of v, it's 1/9 t to the 9th times du, that's 1 over t dt. Now, a lot of students make the mistake at this step of just using the power rule for this piece and then multiplying it by the natural log of the absolute value of t. Don't do that. There is no product rule for antiderivatives. You've got to simplify this first and then take the antiderivative. So that t here, we can think of as in the denominator, and that t to the 9th we can think of as in the numerator. And this t will reduce with one of those, and we'll end up with a t to the 8th. So I end up with a negative 1/9 times the antiderivative of t to the 8th, plus the antiderivative of this piece. Let's just go ahead and do that. Bring the 2 down, add 1 to the exponent, divide by the new exponent. Don't forget your constant of integration. So I end up with this 1/3 t to the 6th over here. And we still have this integral to evaluate. Just a power rule, no big deal. Nothing we can't handle. So I had an x times t to the 7th, that was my integrating factor, and a 1/9 t to the 9th times natural log of t, minus 1/9 times the integral of t to the 8th, yep, that's right. Sorry. And then I've got the 1/3 t to the 6th plus c. Okay, almost done with the anti-differentiation. It's not too bad, it's just long, you know. Once you brush up on your prerequisites, it's not too bad. So we add 1 to the exponent and we divide by the new exponent. And we're there. Nine times 9 is 81. Okay, and all of this is equal to x times t to the 7th. We're trying to isolate our dependent variable, which in this case is x. X is a function of t. So we'll divide everything here by a t to the 7th. And if you want to, I mean, you could divide each of these terms by t to the 7th. It's up to you. So I have x of t equals this 1 over 9 t to the 9th natural log of t minus 1 over 81 t to the 9th plus 1 over 3 t to the 6th plus c, all divided by t to the 7th. Now, I don't like fractions within fractions, complex fractions. So to get rid of those complex fractions, I'm just going to multiply with the least common denominator of the 9, the 81, and the 3, which is just an 81. That's legal as long as I do the same thing in the numerator and the denominator of the whole thing. So I'm taking 81 and I'm distributing it to all of these terms. Here's 1, and there's 1, and there's 1, and then of course that constant times 81. Just going to affect that constant out front. So 1/9 times 81 is just going to give me a 9. And that 81 over that 81 is just going to be a 1. And that 3 goes into 81. Well, remember, 81 is 9 times 9, so that's 3 times 3 times 3 times 3. So if you take out one of the 3's, I'm going to be left with 3 3's, so I have a 27. And a constant times 81 is just a different constant. I'll call that C1. Okay. And this is the general solution of the differential equation. Now let's go back and see if there were any restrictions on t. Well, clearly t can't be 0, and the implied domain here is that t has to be greater than 0 because we can only take the natural log of a positive number. We also use that here. So t has to be positive, and I think that's the only restriction. As I go through the method, the only issue is t being 0 in the denominator or taking the natural log of a positive number, which is necessary. Okay, so this is our solution as long as t is positive. So the interval of existence, maximal interval of existence, would be 0 to infinity. And the second to last step was dividing by the integrating factor to isolate x. So this is the general solution. We always like to state our general solution on an interval. And if we were just asked to solve the differential equation, and many times that's all we're asked to do, we would stop right here and we would be done. But this time we were not just asked to solve the differential equation. We were also given an initial condition. We were told when t equals 1, x should be 0. We can use that to find the right value of c. So we're going to use the initial condition to find the value of c that we're looking for. And it's pretty easy. You just replace all the t's with 1. Just using placeholder notation. And then simplify. Remember, natural log of 1, that's 0. That's what y equals natural log of x looks like, roughly. When x equals 1, y equals 0. So we're on the x-axis there. So this guy is 0. So we end up with -1 plus 27 plus c1, all divided by 81. Or, simplify further, 26 plus c1, all divided by 81, is x of 1 in general. But we were told that x of 1 equals 0. So we have to set this equal to 0 and solve for c1. Okay. Well, if that fraction is 0, you can multiply both sides by 81, and of course you'll get the numerator equals 0. And that means that c1 must be -26. Okay. So x of t is 9 t to the 9th times natural log of t minus t to the 9th plus 27 t to the 6th minus 26, all divided by 81 t to the 7th. And that's going to work on the interval from 0 to infinity. So we used the initial condition to find c, and then we state our particular solution. So you've got to substitute that value of c that you just found into the general solution. So here's my general solution. I just replace the c with the -26. And of course, you want to state your interval of existence I. So that is the solution that we're looking for. And you should be able to check it. You should plug in t equals 1. Make sure you get 0 from that. And if you wanted to, you could actually take its derivative, multiply it by t squared, add 7t times the function, and simplify. And if you do that, if you get t cubed natural log of t plus 2 and x of 1 equals 0, you know you found the solution to the differential equation that passes through the point t equals 1, x equals 0. And that's what we were looking for.